Dear learners, welcome to the another new lecture of e-lecture series of the engineering chemistry. In today's video, following topics we will cover: water softening techniques. Basically, we know about what are the water softening techniques. Then in detail we will going to discuss about lime soda process, which includes basic principle of lime soda process, various type of chemical reactions of lime and soda, cold lime soda process and the hot lime soda process. Now, to begin with, what are the water softening techniques? Basically, the water softening techniques refer to the processes that remove or reduce the hardness causing minerals, mainly calcium and magnesium, from the water. So these are the techniques which are used to remove calcium and magnesium salts from the water. So these methods are designed to make hard water more suitable for consumption, cleaning and industrial use. Why this softening is necessary? Because we know that hard water can lead to scaling, it reduces soap efficiency and other issues. That is why water softening is very necessary step. The common water softening techniques includes lime soda process, ion exchange process, zeolite process and the reverse osmosis. In today's e-lecture series, we will discuss the lime soda process in detail. So, the basic principle of lime soda process. The lime soda process is based on the principle that all the soluble hardness causing salts are chemically converted into insoluble precipitate, which are then removed by settling and filtration. That means all the salts responsible for hardness are converted into precipitate by the reaction of lime and soda, and this precipitate can be removed by the filtration. So in this way, hardness causing salts are removed from the water. So in this process, lime, that is calcium hydroxide, and soda, that is sodium carbonate, are added to the raw water or the hard water, which reacts with the calcium and magnesium salt. These salts are the hardness causing salts and convert them into insoluble precipitate of calcium carbonate and magnesium hydroxide. Calcium carbonate is the most insoluble salt of calcium and magnesium hydroxide is the most insoluble salt of the magnesium. So basically, in the lime soda process, we are adding lime and soda to the hard water sample. By the reaction of lime soda onto the various type of hardness causing calcium and magnesium salts, all the calcium salts are converted into calcium carbonate, which is the most insoluble form of the calcium salt, and all the magnesium salts are converted ultimately into magnesium hydroxide, which is the most insoluble form of the magnesium salts. So in this way, all the calcium and magnesium salts are converted into their most insoluble form. That is why these are precipitated and further removed by the filtration process. So in this way, all the hardness causing salts are removed from the hard water. Now we are going to discuss the reactions of lime and soda. So first we will discuss the reaction with the lime. How temporary hardness is removed by reaction of lime? We know that temporary hardness is mainly caused by the calcium bicarbonate and the magnesium bicarbonate. So when we add the lime to the hard water which contains the temporary hardness, that means which contains the calcium or magnesium bicarbonate, the lime reacts with the bicarbonates of calcium and magnesium and convert them into insoluble form of their respective salts. So looking towards the reaction, when we add lime, the lime reacts with the calcium bicarbonate and forms 2 moles of calcium carbonate and water. So in this reaction we can see that 1 mole of lime is required to remove the calcium bicarbonate. how we can say that it removes the calcium bicarbonate? Because when lime reacts with the calcium bicarbonate, it converts the calcium bicarbonate into calcium carbonate, which is the insoluble form. That means it can be removed by the filtration. So for removal of the calcium bicarbonate, 1 mole of lime is required for 1 mole of calcium bicarbonate, right? Secondly, temporary hardness is caused by magnesium bicarbonate also. So when we add lime to the hard water sample which containing the calcium bicarbonate, it reacts with the magnesium bicarbonate. It reacts with the magnesium bicarbonate and forms magnesium carbonate, calcium carbonate and water. Further, this magnesium carbonate consumes second mole of lime and convert into the precipitate of magnesium hydroxide. So in this way, magnesium bicarbonate get completely precipitated as magnesium hydroxide. But for this complete precipitation, it requires 2 mole of lime. One is this and second one is this. So in this way, magnesium bicarbonate is removed from the hard water sample. So remember that to remove the temporary hardness of calcium, 1:1 ratio is there. That means 1 mole of calcium bicarbonate needed 1 mole of lime for complete precipitation. While magnesium bicarbonate requires 2 mole of lime for its complete precipitation. So magnesium bicarbonate requires 2 mole for complete removal. Now, reaction of lime with the permanent magnesium hardness. We know that permanent magnesium hardness is caused by magnesium chloride, magnesium sulfate, magnesium nitrate, etc. So when magnesium chloride reacts with the lime, it forms magnesium hydroxide precipitate and the permanent calcium hardness is also generated. So we can see here that magnesium chloride requires 1 mole of lime for its complete precipitation, but at the same time it generates equivalent amount of the permanent calcium hardness. Similarly, 1 mole of magnesium sulfate requires 1 mole of lime for complete precipitation, but it generates equivalent amount of calcium permanent hardness as the calcium sulfate. So what we can conclude it from these reactions then, that when we add lime, the permanent magnesium hardness requires 1 mole of lime for its complete removal, but it generates 1 mole of permanent calcium hardness, which requires soda for its removal. So remember that permanent calcium hardness cannot be removed by the lime. For the removal of permanent calcium hardness, soda is required. What is soda? Soda is the sodium carbonate. So permanent magnesium hardness for its complete removal requires 1 mole of lime as well as 1 mole of the soda. Why? Because it generates the equivalent amount of permanent calcium hardness, and for removal of this permanent calcium hardness we requires the soda, 1 mole of soda. That is why whenever in the numericals permanent magnesium hardness is given, remember that it requires lime plus soda for its complete removal. Why? Because when lime reacted with the magnesium permanent hardness causing salts, it removes the magnesium hardness, but it generates the permanent calcium hardness. For the removal of this permanent calcium hardness, soda is required. That is why whenever in the question it is given that permanent magnesium hardness is present in the water, we always mention that for the complete removal of permanent magnesium hardness, lime plus soda both are required. Now, third removal is the dissolved hydrogen sulfide and the carbon dioxide gases from the water. When dissolved H2S and carbon dioxide is present in the water, it also reacts with the lime and consumes the lime. Hydrogen sulfide reacted with the lime and convert the converted into the calcium sulfide precipitate. Similarly, carbon dioxide reacted with the lime and form the calcium carbonate precipitate. And 1 mole of H2S requires 1 mole of lime. 1 mole of CO2 requires 1 mole of lime. That means we can say if dissolved gases like H2S and carbon dioxide are present, these requires 1 mole of lime for their complete removal from the water sample. Now, next is the removal of the free mineral acids from the hard water. The free mineral acids are hydrogen chloride and the hydrogen and the sulfuric acid. So when we added lime to the hard water sample which contains HCl and H2SO4, the lime reacted with the HCl and forms the calcium chloride, which is the permanent calcium hardness, which requires soda for its removal. So whenever HCl is present in the water, we must mention that it requires 1 mole of lime as well as 1 mole of soda for its complete removal. And also it is notified that 2 moles of HCl requires 1 mole of lime. That means if 1 mole of HCl is present, it requires half mole of lime. And when half mole of lime is consumed, half mole of calcium chloride is produced, which requires half mole of soda. So whenever the hydrogen chloride is present, HCl is present, always remember that it requires 1 mole of HCl requires half mole of lime plus soda for its complete removal. And if H2SO4 is present, the lime reacted with the H2SO4 and form the calcium sulfate and the water. The calcium sulfate is the permanent calcium hardness which further requires for its removal the soda. So whenever the H2SO4 is present in the water, it requires 1 mole of lime and 1 mole of soda for its complete removal. While if HCl is present, it requires half mole of lime and half mole of soda for its complete removal. Now, next is the removal of dissolved iron and aluminium salts from the water. If iron sulfate is present in the hard water, in generally we know that in water purification we have discussed that in the coagulation process we are added the iron sulfate and alum for better suspension, for better sedimentation of the water. So in this way, in some water samples iron sulfate and aluminium sulfate also present in the water. So if iron sulfate is present in the water, it reacts with the lime and form ferric hydroxide and generates the equivalent amount of calcium hardness in the water, so which requires the soda again. So whenever iron sulfate is present, FeSO4 is present, it requires 1 mole of lime as well as 1 mole of soda for its complete removal. Always remember that in the reaction of lime, whenever you see that at the product side permanent calcium hardness is produced, so remember that for that removal of that permanent hardness we must add soda for its removal. That is why whenever in the product the permanent calcium hardness is there, we must include soda for removal of that salt completely. So, and further this ferric hydroxide again reacts with H2O and oxygen and forms precipitate of ferric hydroxide. If aluminium sulfate is present, it requires 3 moles of lime for the precipitation of aluminium sulfate as the aluminium hydroxide and also generates 3 mole of permanent calcium hardness. So we can say that if aluminium sulfate is present, so 1 mole of aluminium sulfate requires 3 moles of lime and 3 moles of soda for its complete removal. So 3L plus S is required for its complete removal. Why? Because in this reaction we can see 1 mole of aluminium sulfate reacts with the 3 mole of lime and generates 3 mole of permanent calcium hardness. So for its complete removal, 3 moles of L plus S is required. Again, next reaction is reaction with the sodium bicarbonate. If sodium bicarbonate is present in the water, it reacts the lime and generates sodium carbonate, calcium carbonate and water. So sodium bicarbonate generates sodium carbonate, that means the soda. So whenever sodium bicarbonate is present, always remember that it consumes the lime but it generates the soda. And in which ratio? We can see here 2 moles of sodium bicarbonate consumes 1 mole of lime. That means 1 mole of sodium bicarbonate consumes half mole of lime, which produces half mole of soda. So since here the sodium carbonate is generated in this reaction, so it must compensate the requirement of the soda. So we can say that if sodium bicarbonate is present in the water sample, the requirement of lime and soda is half L minus S. Why we are putting here L minus S? Because L for soda which is used, that means which is consumed, so it requires L. But why minus S is here? Because soda is produced in this reaction, not consumed in this reaction. When soda is produced in this reaction, that means it compensates the requirement of soda. That means we have to add less amount of soda for its water, completely water softening. Why? Because some soda is generated in this reaction. And why we are putting half here? Because 2 moles of sodium bicarbonate needed 1 mole of lime, which generates 1 mole of soda. If we taking here the 1 mole of sodium bicarbonate, so it consumes half mole of lime and generates half mole of soda. So that is why half L minus S is the complete requirement of lime and soda for the sodium bicarbonate. Now some important points which we have to revise, that as we see that for the removal of calcium bicarbonate, it requires 1 mole of lime, but for removal of magnesium bicarbonate, it requires 2 mole of lime. Just see here the reaction. 1 mole of calcium bicarbonate requires only 1 mole of lime, but 1 mole of magnesium bicarbonate requires 2 mole of lime for its complete precipitation as magnesium hydroxide. So calcium bicarbonate requires 1 mole of lime, while magnesium bicarbonate requires 2 mole of lime. Second point, the lime converts the permanent magnesium hardness into the permanent calcium hardness, which requires soda for its removal. See all the reactions here in which magnesium permanent hardness, lime is reacted and generates equivalent amount of permanent calcium hardness, and for removal of permanent calcium hardness, soda is required. So lime converts permanent magnesium hardness into permanent calcium hardness, further which requires the soda for removal. Reaction of lime with aluminum sulfate and iron sulfate and mineral acids also generates equivalent amount of calcium permanent hardness, for which soda is required for its removal. See here dissolved gases. After dissolved gases we saw the removal of free mineral acids. Here we can see in all these reactions permanent calcium hardness is generated, and for removal of this permanent calcium hardness, soda is required. 1 mole of lime is used to react sodium bicarbonate, but it generates 1 mole of soda also. That means we have to subtract the amount of soda from the total requirement, because soda is also producing in this reaction. So basically the precipitate formed as a result of these chemical reactions are very fine particles of PPT are formed. So these may cause troubles by getting deposited on the pipes and boiler tube later. The problem can be overcome by adding the coagulants like sodium meta-aluminate. These coagulants, when reacts with the water, generates the sodium hydroxide and aluminium hydroxide. So aluminium hydroxide basically acts as a coagulant, but it also generates sodium hydroxide. The equivalent of OH minus sodium hydroxide generates the OH minus ion in the water sample. So the equivalents of OH minus ions can be considered to be one equivalent of lime, and hence the corresponding amount should be subtracted from the lime required. So always remember that whenever the sodium aluminate NaAl2 is present in the water sample, it compensates the requirement of lime because it generates the NaOH, and which gives the OH minus into the water sample. So from above discussion, it is very clear that lime is required by calcium bicarbonate, magnesium bicarbonate, magnesium chloride, magnesium sulfate, CO2, bicarbonates, and the free acids and free gases. If weight of all the substance are converted into CaCO3 equivalent hardness, then we know that 100 parts of calcium carbonate equivalent hardness requires 74 parts of calcium bicarbonates. What we are doing here, that putting molecular weight of 1 mole of calcium carbonate and calcium hydroxide. Molecular weight of 1 mole of calcium carbonate is 100 and calcium hydroxide is 74. So 100 parts of CaCO3 equivalent hardness is equal to 74 parts of calcium hydroxide. So in this way we can calculate the total lime requirement for the softening of this water sample. So 74 by 100 bracket 2 into temporary magnesium hardness. Why 2 into temporary magnesium hardness? Because we saw in the chemical reactions that 2 mole magnesium bicarbonate requires 2 mole of lime. That is why 2 multiplied by magnesium bicarbonate or the magnesium temporary hardness plus temporary calcium hardness, that is calcium bicarbonate, plus permanent magnesium hardness, that is magnesium chloride, magnesium sulfate, carbon dioxide, HCl, H2SO4, iron and aluminum salt, bicarbonate, and minus sodium aluminate. Why minus sodium aluminate? Because just we saw here that sodium aluminate is present if in the water, then it generates the NaOH, and equivalent of OH minus ions can be considered to be one equivalent of the lime, and hence this corresponding amount should be subtracted from the lime requirement. That is why we are putting the minus sodium aluminate here. Bracket, all are in terms of calcium carbonate equivalents. So first we have to convert all these salts into calcium carbonate equivalent, then multiplied it by 74 by 100, then multiplied by volume of water and multiplied by the purity factor. What is purity factor? We will going to discuss in after few slides. So this is the complete formula to calculate the total lime requirement for the water softening. Now reactions of the soda. The soda is used to remove the permanent calcium hardness basically, and permanent calcium hardness is calcium chloride and calcium sulfate. It reacts with the sodium carbonate to form the calcium carbonate precipitate, which can be removed for further for the filtration. So whenever we in all those reactions in which calcium chloride and calcium sulfate is formed as the precipitate, we will use L plus S always there for the complete removal. So what are the conclusion now here? That the substances like sodium chloride, potassium chloride, sodium sulfate, silica oxide, iron oxide, etc. do not impart any hardness to water, hence these do not consume any lime or soda. That means if these salts are present in the water, these does not react with the calcium hydroxide and the sodium carbonate. So they do not consume the lime and soda. Second one is the temporary calcium and magnesium hardness do not require soda. Only lime is required for their complete removal. Permanent calcium hardness does not require any lime. For the removal of permanent calcium hardness, only soda is required. Permanent magnesium hardness, that is magnesium chloride, magnesium sulfate, iron and aluminium salt, iron sulfate and aluminium sulfate, and free acids HCl, H2SO4 requires lime as well as the soda. So L plus S is the total requirement for these salts. Presence of sodium bicarbonate requires lime, but it generates sodium carbonate in the equivalent amount, and hence the amount must be subtracted from the soda requirement. So whenever sodium bicarbonate is present, we will use L minus S for its complete removal. Since in some cases the treated water also shows OH minus and the carbonate ion concentration. Treated water is water after the softening process. So after softening process, if water contains OH minus ion and carbonate ions, then it shows that some of the lime and carbonate does not react it in the softening process. So these are formed from the excess lime and soda respectively. So during the calculation, the corresponding amount to these should be added. In case of excess OH minus ions, the equivalent amount is to be added in the lime as well as the soda. Why? Because for the compensation of this OH minus, when we add the lime as calcium hydroxide, so we know that when we add the calcium hydroxide, it also generates the calcium permanent hardness. Calcium is also generated. So for removal of this permanent calcium hardness, soda is also to be added. So whenever in case of OH minus ion, whenever the excess OH minus ions are present in the treated water, the equivalent amount to be added in the lime as well as the soda. Why lime and soda both are required? Because when we added lime as the excess amount, we also added the permanent calcium hardness to the water, and for this permanent calcium hardness removal, the soda is also required. And for excess of carbonate ions, the equivalent amount of soda is to be added to the water sample. So whenever the lime OH minus ion and carbonate ion are present in the treated water, for the compensation of this OH minus, lime plus soda is added, and for compensation of this carbonate ion, only soda is to be added to the water sample. Now calculation of amount of soda required. As we discussed that soda is consumed by calcium chloride and calcium sulfate originally present, and by the equivalent amount of these salts formed by the treating of water with the lime having magnesium chloride, magnesium sulfate, aluminium sulfate, iron sulfate, HCl and H2SO4. So basically whenever these salts are present, these salts also generates the permanent calcium hardness. So for these salts also we have to add the soda. 100 parts of calcium carbonate equivalent hardness requires 106 parts of soda. What we are doing here, we are putting the molecular weight of calcium carbonate and the molecular weight of sodium carbonate here. So 100 parts of calcium carbonate is equal to 106 part of the sodium carbonate. So total soda requirement is equal to 106 divided by 100 bracket. All these salts which are using soda for complete removal in terms of calcium carbonate equivalent. What are these all salts? Permanent calcium hardness, permanent magnesium hardness, iron and aluminium salt, HCl, H2SO4 and minus bicarbonate. Minus bicarbonate, why here? Because we saw the reaction that whenever the sodium bicarbonate is present, it reacts with lime to produce the sodium carbonate in the water, which have to be subtracted from the total soda requirement. That is why minus bicarbonate is putting here. Remember that all these salts are using in terms of the calcium carbonate equivalent. This factor multiplied by total volume of water multiplied by the purity factor of soda. Now, what is this purity factor? If the lime and soda used are impure, then actual requirement of lime and soda is calculated according to their purity. For example, if the lime and soda are 95 and 85% pure respectively, therefore, then the values obtained in each case are multiplied by the purity factor. For lime, 100 by 95, for soda, 100 by 85. So whenever in the question the purity of lime and soda is given, so we have to multiply the total lime or soda requirement by its purity factor. What is purity factor? 100 by its whatever the percentage is given. Suppose 98% lime is given, then we have to put purity factor 100 by 98. For soda, suppose 70% purity is given, so we have to put the purity factor 100 by 75. Whatever percentage is given, so we have to put that purity factor to the all lime and soda requirement. So we have concluded requirement of lime and soda in this table. Calcium bicarbonate requires 1 mole of lime. Magnesium bicarbonate requires 2 mole of lime. Magnesium chloride requires lime plus soda both, because when magnesium chloride reacts with lime, it consumes the lime and generates equivalent amount of permanent calcium hardness, for which 1 mole of soda is required. Similarly, magnesium sulfate and nitrate also requires L plus S, L plus S. Permanent calcium hardness, calcium chloride, sulfate, nitrate requires only the soda. H2S, hydrogen sulfide and carbon dioxide gases requires the lime only. HCl, H2SO4 mineral acids required lime and soda. Iron sulfate requires lime and soda. Aluminium sulfate requires 3 moles of lime plus soda. Sodium bicarbonate requires L minus S. Why minus S? Because soda is produced in the reaction of sodium bicarbonate and the lime. That is why we are putting here minus S. If sodium meta-aluminate is used as the coagulant, then we are putting here the minus L, because when sodium meta-aluminate reacts with the water, it generates OH minus ion, which compensates the requirement of the lime. That is why minus L is written here. Calcium plus 2 ion, that is the considered as the permanent calcium hardness, so only soda is required. Magnesium plus 2 ions considered as permanent magnesium hardness, that requires L plus S. Calcium carbonate requires only lime, because we assume here that calcium carbonate is present in the water due to the calcium bicarbonate. So for calcium bicarbonate, 1 mole of lime is required. Magnesium carbonate requires 2 mole of lime, because we are assuming here that magnesium bicarbonate is present in the water due to the presence of magnesium bicarbonate. I am repeating, magnesium carbonate is present in the water due to the presence of magnesium bicarbonate, and we already seen that magnesium bicarbonate requires 2 mole of lime for its complete removal. That is why we are putting here we are putting here 2L. So now it's time for the learning check. Please read the question displaying on your screen and try to solve it. A water sample containing calcium bicarbonate 162 ppm, magnesium chloride 95 ppm, calcium sulfate 136 ppm. Calculate amount of lime and soda required for 80,000 liters of this water if purity of lime is 95% and purity of soda is 96%. So what we have to do, for the calculation of Lyman required. Always remember that to solve these type of numericals, first we have to form the table which includes 4 columns, that is salt present in the water, the amount of salt given in the numerical, its calcium carbonate equivalent, and lime and soda requirement. So calcium bicarbonate is given 162 ppm. So calcium bicarbonate is the 162 ppm. Next column is the calcium carbonate equivalent. In our previous lectures, I already show that how to calculate the calcium carbonate equivalent of any salt. For this, we have to multiply the amount of that salt by its multiplication factor. What is the multiplication factor? Multiplication factor is the 100 by the molecular weight of that salt. In case of calcium bicarbonate, the molecular weight is 162. So 100 by 162 is the multiplication factor for calcium bicarbonate. The amount of the calcium bicarbonate is also 162 given in the numerical. So we have to multiply it by 162. So answer is 100 ppm. We know that calcium bicarbonate requires 1 mole of lime. Second salt given in the numerical is magnesium chloride, that is the 95 ppm. The multiplication factor of magnesium chloride is 100 by 95. 100 by 95. 95 is the molecular weight of magnesium chloride. So multiplication factor is 100 by 95. This multiplied by the amount of the salt given to calculate the calcium carbonate equivalent. So answer is the 100 ppm. Similarly, calcium sulfate amount is given 136 ppm. The molecular weight of calcium sulfate is 136. So 100 by 136 is the multiplication factor for calcium sulfate. It is multiplied by 136, that is the amount of calcium sulfate, which is equal to 100 ppm. It requires soda only. So the total lime requirement is equal to 74 by 100 bracket calcium carbonate equivalent of calcium bicarbonate and calcium carbonate equivalent of magnesium chloride. See here, only lime is written in 2 columns. So we are included only these salts. Calcium sulfate does not require lime. So we are not including calcium sulfate in this. Multiplied by total volume of water, which is given 80,000 liter, and the purity factor. Purity of lime is given 95. So purity factor for lime in this numerical is 100 by 95. So by putting all these value, finally we concluded that the amount of lime required for this water sample is 12.46 kg. So requirement of soda. Soda requirement is equal to 106 by 100 bracket calcium carbonate equivalent of calcium sulfate and magnesium chloride. See here, soda is written only in these column. Magnesium chloride requires soda, calcium sulfate requires soda. We know that calcium bicarbonate does not require soda. So we included only magnesium chloride and calcium sulfate in this formula, multiplied by volume of water multiplied by purity factor. So finally all the values are putting here. The purity factor is 100 by, this is 98%. So 100 by 98. So finally value calculated by this is 17.3 kilogram. So this is the total soda requirement for this water sample. So thank you so much. That's all for today's video. To unlock more awesome content, you can hit the like button and subscribe my channel. Once again, thank you.